Right. And today already we discussed what is Lagrangian is, and we discussed simple harmonic oscillator problem in previous video itself. And if you want to get understand what is meant by L and what is meant by how we are solving that linear harmonic oscillator problem, just check into my previous video, right? So these two are some practice problems. These are simple problems, right? So here we have a Lagrangian L is equal to of q dot square plus q dot minus of q square, right? Then for this we have a generalized coordinate which is q, and q dot is the generalized velocity. So once we have a generalized coordinate and generalized velocity, we write the Euler-Lagrangian equation using that coordinate. So here I am using q dot and q, since we have L as a function of q dot. So we have to find dou L by dou q dot. Then we have to find dou L by dou q. So dou L by dou q dot we can write. So once you differentiate of q dot square, we'll be getting q dot here, and q dot once you differentiate q dot it will become 1, so I will be writing only q here. Then dou L by dou q, and q is present in these q dot and of minus of q square. Then dou L by dou q is equal to q dot minus q. I am differentiating this L with respect to q, right? Once we have dou L by dou q dot, I have to write d by dt of d by dt of dou L by dou q dot, since q and q dot both are able to we are able to differentiate that. So we are able to write d by dt of dou L by dou q dot is equal to q double dot plus q, because there is no constants here, right? We have to differentiate both q and q dot, right? So we have to write, we can write dou L by dou q term as such as in the previous step. So once I write the final equation using this Euler-Lagrange's equation. So I am able to write q double dot plus q dot minus q dot plus q equal to 0. Here I have a negative sign here. So this negative sign interchange or changes the sign of this term, and we can cancel q dot at q dot. Then we are able to write q double dot plus q is equal to 0, right? So this is our problem. And second problem which we have is L is equal to of x dot square. There is no constants involved, and of x square we have a 1 by 2 in both the terms, right? And here we have d by dt of dou L by dou x dot. Dou L by dou x is equal to 0 because we have a x as a generalized coordinate, x dot as a generalized velocity. And once you differentiate with respect to x dot, we are able to get x dot, and with respect to x we are able to get minus x, right? There's a negative sign here, so we are able to get minus x. And d by dt of dou L by dou x dot, which is written as x double dot, and dou L by dou x is equal to minus x. So you can see x double dot plus q equal to 0. Once you observe these two equations, the coordinates are different, right? If you replace, instead of q as x and q dot as x dot, you are able to get x double dot plus x is equal to 0 here, right? So for a system, for a system you may have n number of Lagrangians. Okay, it should not, there is no limit, or there is no you are not able to control that, but the final equations are important. Okay, whatever may be the Lagrangian is, right? It is able to describe the dynamics or the motion of the system. So that's what important. For a given system, you may have n number of Lagrangians, but you will be ending up with the same equations of motion, right? So we will discuss many things related to this, right? So if you like this video, try to like, comment, and subscribe. Okay. We can discuss some other example in upcoming videos, right? Okay, bye bye, see you.